Hi everybody, I'm Professor Scarpula, and today we're going to talk about the Schrodinger equation. I'm going to take a slightly different tact from the book's treatment, and I'm going to motivate it in terms of some other differential equations which you might be familiar with. So the first one that we'll start with is the wave equation, which you've probably seen in electromagnetics. So it's a partial differential equation, and what we're going to solve for is the wave function psi of x and t. And we're going to look for solutions in a uniform area. And what that means in terms of the wave equation is that the speed of the waves is constant. Okay, so the statement of the partial differential equation is d squared psi of x and t dt squared is equal to c squared times div squared psi of x and t with respect to the distance or x variable. So you've probably seen this in electromagnetics, and you may remember that the c represents the phase velocity of the waves, and that the typical solutions have the form psi of x and t equal to some constant. So if we're talking about electromagnetism, we would represent that as the E field magnitude times exponential to the I kx e to the negative I omega t. And in a homogeneous medium, there's no difference between traveling to the left and traveling to the right, and so we can have the plus and minus signs there. So we call these types of solutions plane waves because we're talking about one dimension, and so the form of the waves is such that the phase fronts move to the left or to the right and are completely the same within a plane coming perpendicular to the direction of propagation. Let me just note one thing, that the phase velocity is in a situation where the phase velocity is constant is simply omega over k. And this even holds if omega is a more complicated function of k. I'm setting that up for a later discussion about matter waves when we get into the Schrodinger equation. Okay, so this is the familiar wave equation. So let me introduce one that you may not have seen, and that's the diffusion equation. So the diffusion equation governs the dispersal of something, say, like if you put a drop of food coloring in a glass, or you can model the diffusion of dopants into a semiconductor. People also use it sometimes for modeling population changes and ideas which can flow through populations. So it's a similar partial differential equation, except the time derivative is only taken once instead of twice. So the diffusion equation looks like this. So we're going to look for some other function. We'll still call it a wave function here, although it's usually referred to as concentration or some other scalar variable. And I wrote out the differential operator. You could also do it in 3 dimension as the Laplacian del squared. Okay, so in the diffusion equation, instead of talking about the phase velocity, which we had in the wave equation, we have this symbol d, which is the diffusion constant. Okay, and let me draw the behavior of something diffusing, and what we'll do is we'll talk about the Green's function for diffusion, or the kernel for the diffusion equation. And that means the response in a homogeneous area to an impulse. So what we'll do is say at time equals 0, we have a Dirac delta function or an impulse of concentration. So we're going to represent the concentration here as this wave function. So this would mean the concentration of food coloring that you put in the glass, or the amount of phosphorus you put in silicon. And then as the time evolves, the diffusion equation basically spreads this impulse out. So what we have to have is that the area under these curves has to be conserved over time, but that it spreads out, and eventually at time equals infinity, it has to be uniform everywhere over the entire domain of solution. So this here would represent the psi of x. So pardon my drawing here, but these shapes can be described as the normal distribution or Gaussian function. So this is the Green's function for the diffusion equation in a homogeneous area. So we can write the solution out like this. And you can see as time goes on, this function here will be a Gaussian function with increasing width. So this width here is given by 2 square root of dt. And then this factor out front is the normalization factor that ensures that the area under these curves is always maintained. Okay. So now we come to our real goal, which is describing the Schrodinger equation. So the Schrodinger equation is somewhat of a combination of these two. It looks a heck of a lot like the diffusion equation. And what it describes is the diffusion of probability of where you might find an electron, for our case, but any elementary particle or thing that you're describing with a quantum mechanical wave function. So what does that mean? In words, it's tied in with the Heisenberg uncertainty principle, that if you know where something is at one moment in time, you sort of don't know how fast it's going, and therefore over time, your knowledge of where it is diffuses or sort of spreads out, and you don't know exactly where it is at a later moment in time. So physically, let's just say we know that an electron is here at time equals 0, but we don't know how fast it's going. And so at times greater than 0, it could be anywhere, but we know, it should be somewhere within a region that might be describable by some sort of Gaussian probability with some width. So the form of the Schrodinger equation, I'll write out the full time-dependent form first, and then we'll, for most purposes, simplify it to the time-independent form for seeking solutions to specific problems. So the Schrodinger and don't forget the umlaut over the O. The Schrodinger equation is like the diffusion equation, except you have to introduce some complex variables. Let's see, h bar squared over 2m. Okay, so let's define the terms here. So the left-hand side is talking about the time evolution. And remember, this looks just like the d by dt side of the diffusion equation, except we've got this complex negative I h bar in front of it. This side looks exactly like the diffusion equation, where before we had a d here, now we've got this thing, negative h bar squared over 2m. And then we add in this extra part here. So what is this? This v of x here is the potential. And it's analogous to the phase velocity in the wave equation. What we can say is that we can solve this time-dependent Schrodinger equation in regions of space where v of x is constant. And if we have that ability, then we can build up more complex functions, more complex situations by solving the Schrodinger equation in piecewise potentials, where v of x is constant over some region and then takes another value in another region. Sort of like having an electromagnetic or sound wave pass from water into air with two different phase velocities. You'll get some reflection and some transmission, et cetera, and we'll see that as we go on to specific cases. So this wave function here plays the same role as the concentration in the diffusion equation, except the fact that it can behave like a wave also, and it sort of, the solutions are sort of in between those of the wave equation and the diffusion equation. Okay, now in physical terms, we can also group this whole side of the equation and just give it an operator notation. We usually use the h with a hat over it, meaning the Hamiltonian operator, and then we say like this. So this notation means that the Hamiltonian operator operates on this wave function psi. And all that means is the Hamiltonian operator gives the prescription, okay, take the derivative with respect to space twice and then hit it with this constant h bar squared over 2m negative sign, and then multiply it by v of x. So we can just define this as like this. And don't be intimidated by this notation. It's just a compact form that sort of gives you the directions on how to take derivatives and multiply by constants. One last note here is note that I explicitly wrote that the potential has to be a function of x only, which means it can't be time varying. There can be situations where considering the time variation of the potential comes into play, but we're going to restrict ourselves for this discussion here to only time-independent potentials, which makes things a lot easier. It does get interesting, though, when you talk about looking at atomic transitions between energy levels, where the potential here could actually be a passing electromagnetic wave. And in that case, the potential is given literally by the electric potential, and it changes versus time. So that gets pretty interesting later. Okay, so that's it for now, our introduction to these three equations. And in the next sections, we'll practice by actually solving these equations in different situations.